Forcing is not going to be able to give her seminar today at 11. And so, and she won't be joining us either today. So Hansi's sick and yeah, so unfortunately she won't be able to give her seminar. So we're going to shift things forward a little bit. We'll have our discussion after the break. So starting around 10 Mountain Time. And then after the discussion, 15 minutes after the discussion ends, we'll have just kind of an informal lunch or tea, feel free to bring food and just chat with colleagues. So we'll keep the Zoom open, and this informal Zoom lunch that we had scheduled at noon, we'll just shift forward in the agenda, and we'll just get a chance, hopefully, to chat with people and see people's faces. So that's the plan. And yeah, I guess, I don't know if there's anything that the other co-chairs, Bill or Jan, or the liaisons wanted to add to that. Nope, everyone looks good. Okay. Okay, so then let's go ahead and get started with the talks. We've got a set of really great talks this morning. So Ariel Morrison is going to be discussing teleconnections between Enzo and Southern Ocean heat uptake. So Ariel, if you can share your screen.
Sure. How's that?
That looks good.
Okay, perfect. All right, yeah, so thank you, Marika. Yeah, thanks to the conveners for setting this up. So what I'm talking about today is probably a little bit more extrapolar than a lot of the talks are going to be, but it's still an ongoing work in progress. So if anyone has any suggestions for things to look at or different methods to use, I would be very interested in hearing about it. Yeah, so this is work looking at teleconnections between strong El Nino events and Southern Ocean heat uptake in multiple CMAP 6 models, including CESM2. This work is funded by the University of Victoria and the DOE's Office of Science through the HiLab project. And it's motivated by a paper that we just published looking at how the atmosphere influences Southern Ocean heat uptake over the historical period in observations. So again, we're looking at the Southern Ocean because of its effects on global climate, how it has accumulated or absorbed a lot of the excess heat and CO2 that's associated with anthropogenic greenhouse gas emissions. And so the recent study that we published was really interested in looking at how the atmosphere is affecting different mechanisms of Southern Ocean heat uptake. Most of the studies that are looking at heat uptake in this region have really just focused on ocean mechanisms. But since we're atmosphere people and we're really interested in clouds specifically, we wanted to see, does this kind of fast moving part of the world affect more slow moving part of the world? And what we found is that there are certain atmospheric conditions that are associated with increased Southern Ocean heat uptake. And those conditions are increased cloudiness and specifically increased cloud liquid water path. So the microphysics of these clouds are more important than just the increased presence of the clouds. And these together are also associated with a more stable lower troposphere. And all of these things together work together to suppress heat from leaving the ocean. So they all work together to increase heat uptake. All of these conditions, however, we found that they were initiated by anomalous atmospheric circulation patterns, and specifically these sea level pressure patterns. So we were looking at these relationships in reanalyses because we would really love to look at these in pure observations, but at the moment, we don't know if there is a good product that has turbulent heat flux observations around the Southern Ocean, specifically in the winter. Again, if anybody knows of the product, I would love to know about it. But this is what we found in reanalyses, that these high pressure anomalies, they're associated with advection that brings heat and moisture into the Southern Ocean from lower latitudes. And all of this, it's linked to a mean reduction of about 30 watts per meter squared that would otherwise be lost from the surface ocean to the atmosphere. And when I'm talking about the Southern Ocean here, I'm referring to the region between 45 and 65 degrees south. So again, a little bit probably more extrapolar than a lot of the talks will be focused on. And I should note that the relationships here are the strongest during the winter and the spring, and we found that they're weakest during the summer. So based on this, we wanted to answer the questions of, is there some large-scale climate phenomenon, such as El Nino, that's causing these circulation anomalies? And then how is that relationship between El Nino and heat uptake represented in climate models? So to address these questions, we're focusing on strong El Nino events in reanalyses and several CMIP6 models. So the data comes from 3 reanalyses, ERA5, JRA55, and MERA2. And again, this is because we really need turbulent heat fluxes, and we haven't found a great observational product for those. We're also using historical CMIP6 data, and all of this is between 1979 and 2014. So the CMIP6 participating models that we're using, there are 14 of them. Each of them have 2 to 5 ensemble members. We've used 4 ensemble members from CESM2. And of course, there's the potential to use the large ensemble a little bit further down the road as well. So given the strong seasonal cycle around the Southern Ocean and the fact that these air-sea fluxes, they're positive or negative, depending on the time of the year, we've split the data into 2 6-month seasons. So there's the heat gain season, that's October through March, and the heat loss season. And these are just defined based on when, on average, heat is either going into or coming out of the ocean. And finally, so since we want to assess the relationships between El Nino and different fields, such as clouds and pressure that are related to heat uptake, we've regressed the detrended seasonal anomaly time series of each of those fields on strong ENSO indices for both of these seasons. For the reanalyses, the ENSO indices come from the Climate Prediction Center, and they are calculated for each individual ensemble member. So each CMIP6 ensemble member has its own unique ENSO index. A strong ENSO index here is anything that's greater than 1. So the first relationship I wanted to check here is between sea level pressure and ENSO. These are showing the seasonal pressure anomaly when the ENSO index is greater than 1 for the reanalyses during the heat gain and heat loss seasons. And so many features are similar between these 2 seasons, most notably the high pressure anomaly. And this makes sense because pressure is less seasonally dependent than heat uptake. However, the heat loss season also exhibits this wave number 3 pattern, and this is pretty consistent with a feature called the Antarctic Circumpolar wave. And this wave advects sea surface temperature anomalies during strong El Nino events from the tropical Pacific to the Southern Ocean. And this has been established before, and it follows the path of the Antarctic Circumpolar current in the ocean. So when we're looking at the CMIP6 multi-model mean, this positive anomaly is still present in both seasons, but this wave is not as strong, and the anomalies are only about half as large as they are in the reanalyses. So I will show all of the different models separately in a couple slides as well. And so the second relationship that we're checking is between ocean heat uptake and ENSO. And during these really strong El Nino events in the heat gain and heat loss seasons, positive ocean heat uptake anomalies are occurring in roughly the same regions as the positive pressure anomalies. During the heat gain season, positive ocean heat uptake anomalies mean that more heat is going into the ocean. During the heat loss season, it means that less heat is being lost from the ocean to the atmosphere. That's just physically what a positive anomaly means in both of those seasons. So as with pressure, the mean heat uptake anomalies for CMIP6, they have a similar pattern. So spatially, the anomalies are occurring roughly in the same places. But again, they're only about half as large as they are for pressure. And as I showed on the first slide, the motivational slide, these anomalous pressure patterns that are associated with strong ENSO, they can advect wind, or they're associated with wind patterns that advect heat and moisture into the Southern Ocean from lower latitudes. And again, this is causing atmospheric changes that reduce heat loss from the ocean to the atmosphere. In addition to that, subsidence from the higher pressure will also suppress turbulent heat fluxes out of the ocean. And that's a really key part of increasing ocean heat uptake during these strong ENSO events. So I'm just going to throw this slide at you. I know it's incredibly busy, but this is showing what the relationships between ENSO and heat uptake and pressure are in all of the different ensemble members that we looked at, and including the 3 reanalyses, which are down in the bottom right corner. And so this slide is really to show the large spread that we found in these relationships in different models, and particularly in the different ensemble members of the different models. And so while the CMIP6 multimodal mean gets this spatial distribution of pressure and heat uptake anomalies more or less correct, there's a really large spread in the values and also where these anomalies are happening. So CESM is actually one of the more consistent models amongst all its ensemble members. And especially in the Amundsen Sea, where it really captures this large positive anomaly in both heat uptake and pressure. And for both of these fields, it has some of the strongest or the most positive anomalies, just go back and forth, of all of the models. And ocean heat uptake is definitely affected by the sea ice edge in CESM2, that kind of stripe close to the continent of really positive anomalies in ocean heat uptake. As a feature that's not very clear in most of the other models, though JRA 55 does show a larger positive anomaly that's also right along its sea ice edge. And so the variability in both of these fields led us to think about why certain models are and are not representing this observed pressure and heat uptake, and maybe how we could classify these different models based on how they represent these relationships. So the final part of this talk is showing some of my initial attempts at classifying the different models. And I'm using a neural net that is trained on the reanalyses to predict ocean heat uptake based solely on sea level pressure. So briefly, I created a convolutional neural net and trained it to predict ocean heat uptake just from the sea level pressure patterns. And this is using monthly anomalies only during the heat loss season, because that's when the relationships are strongest, from 1950 to 2020. And the specific type of neural net that I use is a generative adversarial network. I chose it because it's particularly good for image recognition. And that is essentially what I wanted the neural net to predict. Spatial patterns, specifically, not just the actual values or the magnitude of ocean heat uptake. So all the data that I've used, they're all detrended prior to calculating the anomalies. The anomalies are calculated against 1980 to 2010 baseline. And all of the data are scaled between -1 and 1. And that is required for effective training of the neural net. So these are the actual and predicted relationships on the left and the right between ocean heat uptake and strong El Nino conditions in some of the CMIP6 ensemble means. So again, on the left are the actual Southern Ocean heat uptake anomalies during strong ENSOs. And again, this is for the scaled data, which is why it goes from, not quite -1 to 1. But these values are not as large as you might expect. And on the right are the predicted anomalies based on what the neural net gave us. So first, the predictions underestimate the actual values by about 60%. And second, the predictions can generally capture the positive ocean heat uptake anomaly in the Amundsen-Bellinghausen Sea, but it's not as good at capturing the anomalies elsewhere. So this is indicating that there are some regions of the Southern Ocean where heat uptake has a really strong relationship with pressure, and the predictability is really strong there. And there are some parts of the Southern Ocean that are totally decoupled or mostly decoupled from the atmosphere. And no matter how good the net is at predicting those relationships, is unlikely to predict a correct ocean heat uptake where the ocean is not really responding to the atmosphere. And finally, if we kind of look at different models, one of the models that has a lot of inter-ensemble variability has a really hard time replicating the actual pattern of heat uptake, whereas CESM2 actually does a decent job. The pattern is much more similar between the predicted and actual values. And this is probably partly because CESM2 is actually capturing this relationship between pressure and heat uptake during strong ENSO conditions, but also because there's a lot less variability between the different CESM2 ensemble members, or at least the ensemble members are much more consistent between each other. And since I'm still training and improving the neural net, I'm welcoming any suggestions or feedback on how to improve it. So I'll finish with just a few conclusions. We've shown that positive sea level pressure and Southern Ocean heat uptake anomalies are linked to strong and El Nino conditions. The largest anomalies occur in the Amundsen-Bellinghausen Sea. They follow the pattern of Antarctic circumpolar wave when the ocean is losing heat to the atmosphere specifically. The CMIP6 multi-model mean can capture these relationships, but there's a large spread within individual models and ensemble members. CSM2 is much more consistent across its ensemble members and seems to replicate these observed relationships much better than a lot of the other models. Finally, sea level pressure has some skill in predicting ocean heat uptake in some regions, but it's underestimated generally across all of the models. So, thank you.
Thanks. That was very interesting. I think in the interest of time, because we're at time, I'm going to point people to the chat. So please put your questions into the chat for Ariel. And if you could answer them there, that would be great. And so we'll move on to our next talk, which is from Dave Schneider, looking at, has there been a snow drought in Antarctica? So Dave, if you can just share your screen.
Yeah, can you hear me now?
Yeah.
Okay. Let's see, it's giving me an error that Zoom won't let me share my screen. Try again.
Yeah, it's definitely on. All participants can share their screen. So you should be able to do it from our end at least.
Okay, let's see. I had a recent software update on my Mac.
Whoop.
Yeah, I had that issue when I updated my Mac.
All right.
Yeah,
you might want to go to the next talk. I have to quit and reopen Zoom.
Yeah, or if need be, David, you can send me your slides and I'm happy to present them for you.
Yeah. Okay, maybe we'll move on to Tridata's talk and then we'll come back to Dave Schneider's talk.
Sorry about that.
No, this is part of our virtual meeting world. So yeah, so Tree, if you want to see if you can share your screen.
Well, fortunately, CU updates everything for me, so I think this should probably be fine. Let me just readjust this. Can you see my screen?
Yep, we can see it, but it's in yep, now I can see the full screen.
Okay, great. Back up to the beginning of the presentation. Okay, that's weird. Okay, so that's not showing something, but that's okay. So what I'm going to be talking about today is evaluating a version of CSM, which is a VR CSM over Antarctica. This is a work that's been done with Jan Leonard, Saddam Harrington, Devin Dunmeyer, as well as Jesse Nussbaumer. Whoop. There we go. Okay, so firstly, to introduce what I've been calling the Ansi Grid, and it's basically Antarctica sea ice. This is a spectral element quarter-degree resolution grid within the interior, which is shown here. And it's a 1 degree resolution outside, and it's been rotated to accommodate maximum sea ice extent. So this is the current runs that we have are from 1979 to 2020, and these were forced with observed sea surface temperatures and sea ice concentration. And we also have 3 hourly outputs to be able to calculate atmospheric rivers. And for the 2015 to 2020 period, we've implemented moisture tagging as well. So for the purposes of this talk, we're evaluating the effects of resolution alone. And the way to do this is to compare it with the AMIT model, and that's the Atmosphere Model Intercomparison Project, which for CSM2 has a 10-member ensemble. And what's great about this is that it has the exact same forcing, which is observed SSTs and sea ice concentrations. It's the exact same model, but it only differs by resolution. So for observations, for comparison, we're using ERA 5 reanalysis, station data, as well as a medley reconstruction for surface mass balance. So firstly, to just show off how much more ANSI is able to capture, what I'm showing here is for AMIP and for CSM2 large ensemble, the grid lines are at the 1 degree of resolution, and the spectral element points are shown here in dots. And I'm specifically focusing here on the Antarctic Peninsula because there's a lot of resolution that isn't, or a lot of topography that isn't typically captured. And this makes a huge difference in terms of melt, especially over the Larsen Sea ice shelf over here, which I'll be discussing in a little bit more detail. So here what I'm showing is elevation overall, and this is just from Antarctica. And at the right is the difference in elevation between ANSI and AMIP. And I want to focus on a couple of things. Firstly, obviously, it's resolving much higher topography at the margins, and especially over the Antarctic Peninsula. But it's also lower over ice shelves. So this is kind of important because the resolution is going to strongly impact precipitation, the effect of orography on precipitation. So if I move over. So I'm showing here is surface mass balance, and total surface mass balance values are on the top left, and the difference between ANSI and AMIP are shown on the bottom left. And the first thing we can point out is how much, and I'm just going to roll back here because it's so obvious, is the topography has a really, really strong impact on the difference in surface mass balance. And I'm comparing here the bottom left versus the elevation differences. So what we can see, so the hard thing to tease out here is where has there been an improvement and where has there been an increase in bias. And what I'm showing here on the right is the comparison with the medley reconstruction, and just a small caveat is that has problems in and of itself because it's built off of a reconstruction of ice cores with the MERA 2 model. So this isn't an absolute right or wrong. However, what we're seeing here in purple, I'm showing ANSI where ANSI is improved as compared with the medley reconstruction, and the green where ANSI, the bias is increased. And the main takeaway here is that again, it conforms a lot to topography, but we've seen substantial improvements over the Antarctic Peninsula. And this is both when both AMIP and ANSI have a positive bias, as well as in some situations where AMIP has a negative bias. But East Antarctica, we've seen an increase in bias when, i.e., there's been greater precipitation, a greater SMB that isn't reflected in the medley reconstruction. So we keep going. What I'm showing here is surface melt. And surface melt is compared between ANSI and AMIP again, in the left map over here, and ANSI versus QuickScat here on the right. So in general, on most ice shelves, we've seen an increase in surface melt as compared to QuickScat. So this is sort of enhanced a bias. However, over the Antarctic Peninsula, again, we've seen an improvement. And this is basically showing that AMIP had substantially higher surface melt, especially on the East Antarctic Peninsula. And again, this is very likely an effect of the finer resolution on the topography. So here I'm looking at large scale precipitation, and I'm comparing ANSI minus AMIP again, and this is in summer on the left side versus in winter. on the right, and the comparison of Ansi versus Era 5. And his caveat again is that Era 5 has been reported to have very high precipitation values in general. And so we're going to have to tease this apart a little bit more in the future. But if we focus in on the Antarctic Peninsula here, what we can see is really enhanced precipitation towards the north end and reduced precipitation over the Larsen Sea ice shelf. And this is kind of, I mean, and in addition to this, one of the other interesting factors is this reduction in precipitation just east of the Antarctic Peninsula, which would make sense. So we're going to be looking at the surface here. What I'm showing here is 2-meter air temperature, and it's a comparison again between Ansi and AMIP for summer versus winter. And I'm just looking at the maps here. What we see is enhanced warmth over most of the continent, especially East Antarctica in summer, but some cooling over the Antarctic Peninsula again. But in winter, this effect is just really pronounced. So we can see this enhanced warming of the surface. Now, if we compare this on the bottom side, what I'm showing here is a comparison with 116 AWS stations, where we've thrown out any cases where the elevation differed by more than 100 meters. And in general, the warming has actually improved overall if we average this, but since we're taking this apart by elevation classes, what we can see, and I'm moving here from less than 500, where the elevation of the station is less than 500 meters, all the way to when it's greater than 3,000 meters. And note that we have many more stations available at less than 500 meters. And in general, we've seen a enhancement or a warming in a Ansi overall, except at very low elevations. And the enhanced warming is really, really pronounced at very high elevations. So comparing summer and winter in particular, we can see that in summer, the cold bias that was shown in AMIP has actually been improved at higher elevations, whereas in winter, an already warm bias has been enhanced. So this is a lot of colors, but I'll go through this slowly. What I'm showing here is from top to bottom is geopotential height. And this is an average of over all longitudes between 50 degrees and 90 degrees. So this is kind of a slice moving towards the poles. And the main thing that we can see here is that I'm comparing temperature and specific humidity here. In the summer, we can see the greater temperature over the continent in general, in Ansi. Whereas in winter, and this is a kind of contradictory to the previous map, is that we actually see greater warming in winter in the atmosphere. And take this with a grain of salt. I haven't been able to find a flaw yet in the code. So, but if this is true, this is sort of interesting, and this has a direct effect on specific humidity as well. So you can see that, especially at higher elevations, you have enhanced humidity by like close to about 20%. So here we're focusing on cloud liquid water content and on the left, and cloud liquid ice content on the right. And here we see some major differences. There's a little bit of variability between longitudes here, which I'm not showing just because it's too much information. But we can see in summer is we have far larger cloud liquid water path at lower elevations and somewhat higher cloud liquid water path over the higher parts of the continent. And in winter, this is sort of altered because cloud liquid water path is somewhat lower overall, like near the surface. Cloud ice, on the other hand, we're seeing, and this is the scales here are wildly different. So in cloud liquid water path, this is negative 100%. This is a relative value. So this is Ansi minus AMIP over AMIP as a percentage. And so while on the left it's 0 to 100, on the right what we're showing is negative 300% to 300%. So this is a lot more cloud ice within Ansi as opposed to AMIP. So that's actually fairly interesting. So that's going to have a direct impact on the radiation balance. And what I'm showing here is the comparison between Ansi and AMIP again in summer and winter, but also a comparison with Ansi versus Era 5. And what we can see here in summer is that you have this sort of reversal of a pattern. And what's happened, what this means is that especially in East Antarctica, it's actually erasing a bias as compared to ERA 5. It's a little bit more complicated in winter because you have this sort of division between in West Antarctica where you have an enhanced downward long wave radiation over West Antarctica, which is essentially making the bias worse. And of course, the Antarctic Peninsula is where you have a reduction in that actually is reflected in the NC versus ERA 5 bias. Now, if we look at downwell shortwave radiation, this is kind of an inverse of what we're seeing with downwell and short long wave, especially in East Antarctica. But again, it's about the same thing where we see an increase in downwell shortwave radiation, especially over the peninsula and West Antarctica. This is actually erasing a bias with ERA 5. So it's possibly a general improvement. So as a summary of this evaluation, some main points here is you have a better capture of SMB over the Antarctic Peninsula. SMB changes over West Antarctica and East Antarctica are also strongly impacted by orography. Ansi is warmer, which is an improvement at lower elevations and an enhanced bias at higher elevations. And that has different impacts in summer as opposed to winter. And the shoulder seasons are essentially a reflection of that. Ansi also partially corrects the radiation balance. And finally, the changes to resolution affects moisture profiles over the ocean as well as over the continent. So in terms of next steps, we want to compare moisture profiles of the ocean to observations to be able to figure out exactly what's right here and whether that changes over seasons. And finally, to provide a comparison of SMB estimates to those from regional climate models, such as Rockmell and Mar, which are typically forced at the boundaries by ERA 5 or MERA 2. So just adding a couple of other things that we'll be focusing on using the Ansi Grid is first enhancing resolution. So that's something I'm doing now. The second is we've calculated atmospheric rivers in these simulations because they're available at 3-hourly outputs. And this is adapting an algorithm by Jonathan Willey to a unstructured grid. And finally, implementing moisture tagging. So the moisture tagging was primarily to look at a sea ice decline that started in 2014 and reached a minimum in 2017. And this is just from NASA Earth Observatory, except never mind. So over the last few months, we see this is courtesy of Zach Leb, who, if nobody knows, provides a really interesting Twitter feed of what's happening right now in climate. So this has become even more relevant. And to just give a picture of the moisture tagging map. So moisture tagging was implemented from 2015 to 2020 in model outputs. And this is an original moisture tagging map from Wang et al. In 2020. And what I'm showing right is the moisture tagging map that was implemented in ANSI, so that there's a lot more, there are a lot more tags that are closer to the continent. And this was hugely helped with by Adam Harrington and Jesse Nussbaumer. And just to give a picture of what kind of a difference this can make. So I'm focusing here on the Larsen Sea ice shelf, here on the right, and the Thwaites waste divide. So what these bar graphs are showing is the relative contribution of moisture within just these regions over the 2016 to 2017 period. So we can see major differences. I'm not going to tease this apart. I know it's a lot of colors, but it can just give it can perhaps help us articulate exactly what produces changes in moisture sources. And that's it. That's my main time.
Great, thanks so much. It's really exciting to see this research with these high resolution versions of CESM. So it's great to see. Again, I think we might just stick to the questions in the chat since our talk times are quite short. So if you have questions, please enter them into the chat. And it looks like we actually now have David Schneider's talk, although it just disappeared.
All right. I think I got it. Can you see it now?
Yeah.
All right.
That looks good. It's not in full screen mode, but it's there.
All right, we got full screen now.
No.
No?
Not.
Yeah.
Well, sometimes it, yeah, we're still seeing.
Sorry about that. One more time here.
That looks great.
All right, perfect. So sorry about the technical difficulty. So I'm going to talk about understanding Antarctic snowfall variability. And this is going to be kind of a bigger picture, broader overview than the previous talk. This is in collaboration with this great group of colleagues at the University of Colorado Boulder. And there's also a recent contribution from Gemma O'Connor at the University of Washington. So specifically, I'm going to look at the role of atmospheric circulation in snowfall variability. And so why do we care about the atmospheric circulation? There's 58 meters of sea level equivalent stored on the Antarctic ice sheet. And the atmospheric circulation is basically the mechanism by which the moisture gets to the ice sheet. And then so 6 millimeters of sea level equivalent falls as snow on the ice sheet every year. And that's represented by these white arrows here. And so with climate change in a warming world, one of the things we could hope for, there's not a lot of things to hope for in the warming world, but one of the things that could happen is that there will be more snowfall on the ice sheet. And that could be expected because the atmosphere will warm, having a greater moisture holding capacity. The ocean surface will warm, the sea ice will retreat, there'll be more open water, so more evaporation. And so you could have the potential for more moisture in the atmosphere and more moisture transport to have more snow over the ice sheet. However, there's some spoilers. These other parts of the surface mass balance could change, so you could have more melting that could offset any gain that you get from more snowfall. And you could also, it's not clear to me that the atmospheric circulation will necessarily change in a way that allows for more moisture transport and more snowfall. So in this talk, I'm going to take a kind of retrospective look and see how the atmospheric circulation has changed over the 20th century and what that has meant for snow. So first, we're going to look at 3 time series. And these are 3 different estimates of Antarctic precipitation change over 1900 to 2000, roughly. And the first one on the top is from the CESM2 fully coupled model, the historical run with CMIP 6 forcing. And so it has this period for almost 80 years where there's a relatively weak upward increase in snowfall. And then after about 1970, the snowfall rate really takes off and increases quite significantly. And broadly, this corresponds to a relatively weak, if you look globally, there's relatively weak global warming in the model during this time period. And then it really increases once ozone depletion. So one of the major forcings that's relevant for Antarctica is the ozone forcing. So that's when the snowfall really increases in the late 20th century. In the middle panel is the GOGA run. So this is like an AMIP style run with prescribed SSTs and sea ice from observations. And this is broadly similar to the coupled run in that there's this period of relatively small change, and then there's this big increase, and then it levels off after the year 2000. So if you look at observations, such as they are, in real life, a big increase like this has really only occurred on the Antarctic Peninsula. It hasn't occurred over the ice sheet as a whole, as far as we know. So in the bottom panel, we have sort of our best estimate of what has actually happened. So this is from Brooke Medley and Elizabeth Thomas, their reconstruction based on 53 ice core records. And this is technically accumulation, not precipitation. So accumulation, this is what actually accumulates on the ice sheet versus what falls. So for the purposes of this talk, I'll just compare them directly. But if you want a more perfect comparison, look at Devin Dunmeyer's upcoming paper. So you'll be able to compare these things in terms of surface mass balance rather than accumulation versus precipitation. But generally what the observations show is that there's been a relatively small upward trend in accumulation over the 20th century. It looks pretty small, but it does over time translate into 10 millimeters of sea level offset. So it's not insignificant, but it is much smaller than the CSM2 is suggesting. So now we're going to look at the same set of results, but in map view, and I'm going to add in the circulation change that goes along with it. So on the left, we have the Medley and Thomas accumulation change over the 20th century. And you can see most areas show an increase. The largest increases in the Antarctic Peninsula. And then there's this one region around the Eastern Ross Sea where there's been a decrease in snowfall over the 20th century. And then on this map, I plotted sea level pressure contours. And this is from a new results using paleoclimate data assimilation from Jim O'Connor led this work in collaboration with Greg Hackham and Eric Steig at the University of Washington. So this is their circulation reconstruction mapped on top of the Medley and Thomas snowfall reconstruction. And so you see kind of generally this southern angular mode type pattern, and embedded within that, there's this big low pressure center, which we might call the Amundsen Sea low. So that has deepened over the course of the 20th century, and it's contributed to this dipole pattern in the snowfall trend. So if you know your West Antarctic topography, this is where the waves divide is. And so you have a windward side where there's more snow, and then you have a leeward side where there's less snow. And then over East Antarctica, there's relatively small changes overall compared to West Antarctica and the peninsula. So most of that small increase in overall Antarctic snowfall has come from this peninsula region. And so in the middle panel, we have the CSM2 fully coupled simulation. It's ensemble mean. So it generally shows an increase everywhere, especially along the coast. And there's not a really strong trend in the atmospheric circulation overall. And then on the right, we have this prescribed SST simulation, the GOGA simulation. And it has the same external CMIT6 forcing as the coupled run, except we're using, instead of a fully coupled ocean, we're using prescribed SSTs. And so this kind of gets the idea that there's this trend in the Amundsen Sea low, but it's in a really different shape than what this reconstruction suggests. And it's still, East Antarctica looks very much kind of like the fully coupled run. So overall, GOGA is not, I was hoping it would get us closer to what the observations were, but it just doesn't seem like enough of a constraint to really get us there. So there's various ways to kind of characterize those atmospheric circulation patterns and get a time series of the atmospheric circulation. In the interest of time, I'll just show one index, which is a wind speed index over the Southern Ocean from these same three sets of data. And the point is that they all show kind of a general increase in wind speed over the 20th century, but their timing is all very different. So there's this kind of slow upward trend in the coupled run. The go-go run shows more variability with a pretty strong uptake at the end. And then this data assimilation results. So it's a pretty big trend between like 1940 and 1960, and then kind of levels off. And that doesn't correspond with any kind of known big change in forcing. It doesn't correspond with like the ozone hole or something like that. So I'm unsure at this point how to interpret the cause of that jump in the middle of the 20th century. So what we're going to do now is kind of calibrate. We're going to use the model to calibrate the precipitation response to circulation variability. So I'm going to use these definitions of jet strength and jet position from Thomas Bracegirdle and apply them in the CSM2 pre-industrial control run. So two indices, jet strength and jet position. So the jet strength is just the wind speed, and the jet position is the latitude of the maximum wind speed in the zonal mean. And we can regress those onto precipitation and give potential height and quantify the precipitation response for each season. So if we do that in each season, for a positive anomaly, 1 standard deviation anomaly in the jet strength, this is the result that we get for each season. And you see these kind of spatially variable patterns in the precipitation, and then you can integrate them over the ice sheet and see what you get. So the biggest numbers are in the non-summer months, March, April, May, JJA, where you could get these negative anomalies of 24 or 19 gigatons. So this is just one, just for one episode or 1 standard deviation. So if you had a sustained increase in the strength of the jet over a number of years, then cumulatively that could add up to a fairly large snowfall offset. And then with the jet position index, it's kind of the opposite, where the largest anomalies are in the spring and the summer seasons, and they're positive anomalies. So as the jet moves poleward, the storm tracks tend to move poleward, and that gives you more snowfall along the coastal areas. So these are kind of the open questions that I want to answer in the near future. So given our best estimate of the actual atmospheric circulation history, how much did the atmospheric circulation mitigate the Antarctic precipitation trend? And then second question is, why does CSM2 overestimate the 20th century precipitation trends? What I don't know yet is whether these observed trends are actually within the model's internal variability. So in summary, the circulation plays a large role in the precipitation variability, even on the centennial scale over the 20th century. The CSM2 force response overestimates the precipitation trend, and these are a number of reasons why it might overestimate that trend. I had been optimistic that prescribed SST experiments would constrain the circulation trend, but they don't really seem to provide much constraint on it. And so I'm turning to this paleoclimate data assimilation method, which looks like a viable path for constraining the circulation history and its role in the precipitation trends. So thank you. Stop there.
Thanks, David. Interesting stuff. So I think, given that I've started the questions in the chat, I think we'll stick with that, and that way we can regain some of our time. So if you have questions for David, please put them in the chat. I think there's some there already. So we'll move on to Alice DeVivier's talk, which is looking at Antarctic polynyas.
All right. Does this look okay to everyone?
It looks great.
Okay, I'm moving all the people so I can see. Okay, so I think I probably know almost everyone on the call, but I'm Alice and I'm a project scientist here at NCAR. And what I'm going to talk to you about today, as Marika mentioned, is looking at Antarctic polynyas and their impacts on biology. So this is part of a larger project funded by NASA, trying to understand which parts of the Antarctic coastal regions might be valuable for protection. And one of the reasons I have this image here is it's a really good image showing several polynyas around the Ross Island region. So this is Ross Island right here, just for familiarity. McMurdo Station is this tiny little thing right off this peninsula. And you can see this really big polynya out here. This is the Ross polynya, but you can also see some other polynyas here. You might categorize this as a polynya as well, this smaller area off Ross Island, and then kind of hiding underneath the shading here, this is the Terra Nova Bay polynya. So basically what a polynya is it's an area of mostly open ocean that's surrounded by sea ice. So you can see there's sea ice basically all around these three polynyas. And this work is in collaboration with people at CU, Boulder, Woods Hole Oceanographic Institution, and other nonprofits. And I'm just going to be talking about a small facet. So one of the reasons we're really interested in polynyas is that they're areas of high ice production. So in this map that we're seeing here of the whole Antarctic continent, where there are purple colors, these are areas that within our model, we get really high sea ice production. And they happen to be co-located primarily with areas where we know that polynyas exist. So basically what happens in the wintertime, especially when you have winds that are blowing off the continent, they blow ice away from the coast. You get an area of open ocean, you have really cold air above it, you instantly form more ice. And so these areas are kind of sea ice factories where you produce ice and then advect it northward, extending the ice edge. They're also really important for biological systems, as they are an area where biology can either access the ocean or access the air, depending on which side we're thinking about for biology. And they're the first areas that are likely exposed to sunlight when the sun comes back after the Antarctic winter. And so they often have like a phytoplankton bloom before other areas of the continent. So as I mentioned, this project, we're looking at areas that are maybe potentially valuable for protection by CAMLAR, the organization that sets marine protected areas. And what this blue shading indicates here is an existing marine protected area, or MPA. You can see there's another little one up here kind of north of the peninsula. And then there are several other proposed MPAs that exist around the continent. And some areas where there aren't any proposed MPAs either, which has a lot to do with not having data that would be valuable for proposing an MPA. So our goal is to try to understand how polynyas within many of these different regions impact the biology and how they might change into the future and how therefore they might want to be protected. So I'm going to focus primarily on the Ross Sea. That's this sector right here for the rest of this talk. We are looking at other areas, but it's just too much to talk about all the areas in this length of a talk. So one of the things we've done is we've looked at the relationships that we have in CESM, where we have modeled sea ice and we have modeled biology. And we want to understand the relationships between physical and biological systems. So what these maps are showing right here are correlations of the total winter polynya area in the Ross Sea. So we look at how much area is classified as a polynya over the entire year, add that up, and then correlate that with the production the next summer of biology at all the different points. And so what we're looking at here is big zooplankton, and here on the right is diatom primary production. And the red indicates that there's a positive relationship at many of these points between the total winter polynya area and production at those points. So this suggests that having more polynyas, at least in the Ross Sea region, might lead to increased production at lower trophic levels. And then there are implications with this on trophic transfer through the rest of the system. So up to like whales and penguins and charismatic megafauna. These are ocean ice configurations of CESM that were forced by the JRA 55 reanalysis with BGC, and we're expanding this to look at CESM2 large ensemble simulations as well. I also want to talk about how we usually identify polynyas. So Laura Landrum has done a lot of work on this, and so she's really the one who could talk most about it. I'm just going to give you a very brief, broad overview. But a lot of times how you do this is you use some sort of threshold. So if you're using observations to identify polynyas, the only long-term observation we have is basically sea ice concentration. So you'd set some threshold, for example, 85%. And anytime a pixel or a grid cell is below that threshold, you would identify that as a polynya. And there are some nuances with, it needs to be along a coast and bounded by ice around it. So these are coastal polynyas here, whereas if you had somewhere out here in the open ocean, that might be an open ocean polynya. So we have done this. Laura has tested a whole bunch of different metrics looking at sea ice concentration with the observations, and she's also done this with CESM using concentration, and we're starting to explore sea ice thickness as one of these metrics as well, because in the model, when you have an area that's open ocean and you freeze ice right away, the concentration in the model might be 100% even with very thin ice, whereas a satellite might identify that as open water. So there's a lot of nuance with how one identifies polynyas, but we've been exploring this a lot, and Laura is really the expert. I just wanted to point out too that we are trying to look at satellite observations to identify when there's thin ice or ice less than 51 centimeters. And it does overlap well with areas that were identified as polynyas using a concentration metric as we derived here. But what I'm going to talk to you about more for the rest of this talk is I'm interested in seeing if maybe instead of using thresholds, we might be able to use machine learning, specifically self-organizing maps or SOMs, which I know is really confusing for many people here who use the slab ocean model. But we want to use these self-organizing maps to identify polynyas and understand driving processes, maybe without these thresholds. So the science questions I'm trying to answer are, how and why are polynyas changing over time in the Ross Sea during winter? This is not exclusive to the self-organizing map. What are the dominant atmosphere, ice, ocean processes, and do these change over time around polynyas? And then what are the implications for biology? All right, so what is a self-organizing map? Some of you might already be familiar with this, but I'm going to give a brief overview as well. So a self-organizing map is an unsupervised neural network algorithm. You provide training data, which is basically a bunch of vectors or a bunch of times with some variable. And then it uses all of those training times to generate a map of over some space of what the data look like. You have to provide the shape of, or how many patterns you want it to identify. So in this SOM right here, you can see there are a lot of different dots. Those are different patterns that it would be identifying. And we test a lot of different sizes during the training process. You also test a bunch of hyperparameters. So it's a pretty long process to determine what sort of SOM you want to use for science. And then after the SOM has identified like the range of space that your data encompasses, it assigns each input data vector to a particular pattern based on how similar that pattern is to all those different nodes. So I think about this as if you had a whole bunch of maps of like sea ice concentration, as you see here, you would maybe say up in this part of the SOM are times when it's summer and you have very little ice. And so a lot of those dates would maybe be assigned up here, and that occupies summer space. And then if you had winter, when you have very extensive ice, the variable you use to train this might be sea ice concentration, but those would get mapped to the other side of the SOM that represent like the opposite sort of pattern. I also want to point out that this isn't really a new technique. It was developed in the 1980s by Tuovo Kohonen, who I read just died in like the last year. But I hadn't really seen it used with weather climate data until more recently, like the 2000s. So it's not anything super groundbreaking. It's just kind of a new application, I would say, of a method. So what I did for this particular study, so I developed a new Python-based SOM workflow. I've used SOMs in the past in my PhD in a very different context, but I worked with Maria Molina here at NCAR to develop this Python-based workflow. We're training our SOM with data just over the Ross Sea. So these dots right here, the coastal points where we might see polynyas, that's the data that we provide. We're using 25 members from the CESM2 large ensemble, so only half, so that if we want to test our algorithm or we want to test our self-organizing map, we can use the other half and see if it maps similarly, which it should. We're using data from 1980 to 2080, daily winter values, so July, August, September. And then we tested looking at the ice concentration, the ice thickness, and then multivariate testing where we used both of those variables as well. So you can see this leads to over 200,000 different individual dates that are used to train this SOM. So there's a lot of data going in to make sure that we capture the total space, the way that sea ice might look along this coast in the winter. I will also point out, once you test the possible winning SOMs, this is a whole process. So we tested different grid sizes, a 3x3, a 4x4, and a 5x5. So 9 patterns, 16 patterns, 25 patterns total that are identified. And within each one of these, you test a whole bunch of hyperparameter combinations. So like how fast the algorithm learns, and how quickly or how rapidly you want the function where neighbors influence each other to drop off, all of that sort of stuff. And then what you get out at the end is something called Q error. And this is just for the 3x3 SOM, but I've mapped the Q error for all those different combinations. So over somewhere around 90 combinations for just this one size. And we take the lowest 10, and then we look at what is called the Salmon Map. So if you look at the different nodes, you can map that onto space. And what you want is a flat Salmon Map. So you can see this one right here, even though it has a lower Q error, it's kind of twisted. And that makes interpreting it very complicated, because patterns that are supposed to be different may not actually be different if it's sort of a twisted map. So you want something that looks more like this, a flat Salmon Map, where very different patterns are clearly like apart from each other, so that you can physically understand what's going on. So what does the sea ice look like for our SOM that we chose after all this training? So we ended up choosing a SOM that was developed using both the ice concentration and the ice thickness. And this is what the nodes look like. So after we've developed the SOM, and then we make composites of each one of these nodes with all of the data that had been mapped to that node based on similarity. And so you can see that up here in the upper right, we have times when the Ross Sea is basically all ice covered. And then at the opposite side, we have, in terms of ice concentration, what I would identify as the polynya. And then the nodes around it are also polynya-like, where you have lower ice concentrations, these blue colors right along the coast where the Ross polynya happens. So in this sense, the SOM has been successful in identifying a polynya. As I said, we did multivariate training. So if we look at the sea ice thickness that was also trained, you can see that in this particular node where the polynyas happen, we have very thin sea ice in the same area where we get the polynya. But you can see that sea ice is thin kind of in the polynya region in all nodes. So the combination of that sea ice thickness and sea ice concentration seem to be the best for actually identifying physically meaningful patterns in terms of what a polynya is. So now that we've identified our SOM, I'm kind of extending this analysis now. I'm still kind of early on, but I'm looking at things like how often does the big polynya pattern happen? I'm calling it just the big polynya, so we'll just think about this one node with the star. So overall, that particular node happens about 11.6% of the time in the whole data set. But if we break that down by decade, which you can see here, you can see that actually earlier on in the 1980s, these big polynya type features happened around 20% of the time, and that frequency has been dropping off. And then when you get to more like the 2080s, it happens less than 5% of the time. So there are changes in the frequency of this sort of pattern happening, and we're trying to understand how the processes shift or why the frequency changes. I'm not showing it here. We did break down by month instead of over the whole winter season to see if there's like a seasonal shift. There is not. But in addition to looking at just the frequency changes, you can also look at coincident times, what different processes look like. So this is a little hard to see, but this is ice growth processes during one of these big polynya events. And this specifically is congelation ice growth. And you can see that right when there's a polynya event happening, you get a lot of congelation growth, but it's actually offset a little bit from where we saw the polynya, which was right here. So that's really curious to me. I'm not really sure why that's the case, and that'll take a little bit further exploration. And it's also interesting to me that I'm not showing it here, but frazzle ice production is also not coincident with the polynya during these polynya events. So I'm starting to explore both changes in time and changes in processes, but this is still really ongoing work. So I'm just kind of presenting this work in progress. It seems like the tool is working to identify polynyas and processes, which is exciting because we didn't necessarily have to set a threshold ourselves about what is a polynya. And we're really looking at how this changes in time. And eventually I'll expand this to regions beyond the Ross Sea, but we're starting here with the Ross Sea. So I think that's it. If you have any other questions, please ask me in the chat or get in contact in any other way.
Great. Thanks, Alice. It's good that the Polar Climate Working Group is going into biology a bit, so that's nice. So now we're going to have a talk from Monica Morrison, also talking about a little bit different aspect of polar climate research, and specifically talking about actionable science. And she has a friend with her who's going to help.
Sorry, he decided it's optimal time for pets, right as I'm about to speak. Yeah, perfect timing. Okay, hold on one second. Let me get this up. Okay, and does that come up as full screen for everybody?
It looks good.
Yeah?
Yep.
All right, cool. So I'm Monica Morrison, an ASP postdoc in the Climate Global Dynamics Laboratory at NCAR. And today I'm going to be talking about research I'm doing on the concept of actionable science in the context of climate research. And I would just like to note that this is still a work in progress. So these are some like preliminary findings, if you will. So I want to quickly give you an idea of who I am and the approach I'm taking. So I'm a philosopher of science. So my methods for investigating actionable science are to engage in like meta-analysis of the literature. And from that kind of analysis, I identify conceptual themes and then analyze those themes to produce a concrete unified definition of a concept. Then I go about identifying the fundamental components of the concept to translate those to a set of necessary conditions for determining when something actually is actionable science. And from there, I develop a set of recommendations for practice that gives advice to researchers on how to actually satisfy these criteria for actionable science. And it's that perhaps is the most important aspect for climate researchers. So what is actionable science? What are the elements of this like concept that we keep hearing about? Well, I found that there are two dimensions along which actionable science can be characterized. The first is in terms of an actionable research product, which can be a set of data, collection of projections, simulations, figures, geospatial maps, something like that. And the second is in terms of a research process, which is the set of practices that results in that actionable knowledge product. And when we're talking about the product, the necessary features are that the product is useful, which refers to the product having the correct knowledge content for the stakeholders or the users. And then there's also the usability of the product, which refers to the contextual fit of the information that's meant to be used in specific environment or context. And then when we think about the process, the important features are the values that are instantiated during the process, and then the mechanisms or activities that lead to the development of the product and instantiate those values. So when we break down the components of the product, we see that a product is useful when there's consistency, logical consistency between the question and answer. In other words, the form of the answer matches the form of the question. So we make sure that the research questions we're asking are actually consistent with the use questions of stakeholders. And additionally, a product is considered useful when it's adequate, where adequacy can be understood in terms of empirical, representational, conceptual, theoretical, or pragmatic adequacy, or all of the above. And then usability, which is that second branch of actionable products, consists of meaningfulness, appropriateness, and consequentiality. And a scientific product is meaningful when it is interpreted in a way that makes sense for a user who's working in a specific environment or context. A product is appropriate when it fits in with the institutional, cultural, and social situation of the user. And then a product is consequential when it provides information that makes a difference to the decision context and provides more value for the user when they're making their decisions. And so when you're working with users and stakeholders to produce something actionable, you can kind of think of usefulness as the information being produced through the research, being able to answer the kind of what information they need, whereas usability is more that we adequately address how they're going to be using the information. And then usefulness and usability, also we're addressing the why they need information. So what value the information has, and making sure that the information actually meets those conditions for being valuable within their context. Now, we can take these components and provide a set of criteria for determining when we've actually developed a product, a scientific product that's actionable. And I've identified at this point in my analysis 5 necessary criteria for an actionable science product. And they actually kind of map onto those components that I identified a minute ago. So the first is that the logical form of the question and answer need to match up. That means that we essentially need to provide information that captures what the user wants to know, but also why they want to know it. There's a tendency in science for there to be certain assumptions when we formulate questions based on the perspective that we're coming from, and we need to be sure that we're adequately capturing the assumptions of the users in the way that we're formulating the questions, as opposed to our own kind of assumptions and perspectives. And that'll ensure that we produce the right form in our answers to adequately answer questions. Product must also be adequate, where the conditions for adequacy, whether it be empirical, representational, theoretical, are shared between the researcher and the user or the stakeholder. And they're relative to the use context. The product also needs to be translated or interpreted without a loss of adequacy or content. In other words, it needs to make sense to the user and have value within their specific context. And this is where knowledge translation techniques can be really helpful. The product has to fit the norms and situation of the user. So in other words, it needs to kind of reflect the rules and norms of the institution that they're working in. It needs to fit into the way that they structure their decisions and use information in order to make decisions within their institution, culture, or social context. And then lastly, reflecting consequentiality, the product must provide value in terms of information beyond whatever information is already available. And this can mean that you provide more accurate information about some metric that's deemed a priority for their decision-making, or it might mean making certain uncertainty analyses more accessible for some set of projections. What all of these mean is going to be relative to the project. And so these are kind of just abstracted from anything specific. To quickly turn to the elements of an actionable process, where we have a set of values that need to be instantiated. We need credibility, things like trust, transparency, and equity. And then there's certain actions that we can take to make sure that these values are instantiated. For example, bilateral knowledge exchange. So rather than taking information from our research and just kind of handing it over to the user, we engage in a co-creation of information. Communication is central, as is iteration of activities and processes. And so not just kind of this, let's speak to them at the beginning and let's give it to them at the end. There need to be constant kind of recursive conversations about certain things. And then there's integration, where you have unification of knowledge from different perspectives. And more specifically, with respect to these mechanisms, there's certain frameworks for research activities that can ensure we engage in these actions and that we're actually living up to these values. And these are things like the frameworks for co-creation, development, and production, things like structured dialogues, joint decision-making, and shared learning activities. And then similar to with the product, there's certain criteria. So for example, assumptions need to be made explicit, and early structured dialogues can help with this type of thing. When decisions are made throughout the process, they need to include all parties. This ensures equity and transparency. And this includes when we make decisions about things such as the representational features or the parameter choices in the model, if possible, simulation setups, the construction of metrics, stakeholder and researchers and any other party's perspectives should carry equal weight for the most part when making certain decisions, and we should be open to adapting our perspectives, our research perspectives that we bring to the perspectives of the users or the stakeholders. And as I said, exchange of information, this is really important, must be bilateral, not authoritative. So information shouldn't be handed to stakeholders or other participants or partners in the project. It should be actively developed with them. Okay, so what are some of the activities we might engage in our research that actually meet this kind of abstract criteria I just discussed? So here are some examples of what this might look like. So with respect to early stages of research, mainly defining the system and the problem and then designing a research project, one might choose to engage with stakeholders in developing a shared description of the problem. For example, you might work with communities who are engaging in coastal restoration projects, who have concerns about the sustainability of their programs under sea level rise, and construct a joint management, social, and scientific definition of the problem. Similarly, researchers can work with local stakeholders to identify and understand local priorities and value systems, to co-create scenarios and determine approaches for investigating relationships between Arctic warming and future food security for Indigenous communities. And then you also might engage in the co-creation of metrics for model outputs and translation of those metrics to some kind of qualitative form to adequately articulate possible risks to local infrastructure from changes to extreme precipitation events under future climate. A lot of this has been abstract. And so what I want to end with is some preliminary practical guidelines for research that can aid in a project's ability to meet the criteria that were mentioned on earlier slides. So with respect to designing a project, and these are actually meant to be linear, you should begin with the identification of a problem according to the stakeholders, and then engage in a joint description, like create a joint description of the problem that includes both information coming from your stakeholder groups, whether it be management, social, and scientific. Once you've done that, had these initial discussions that can be used to frame the problem in terms of the information that they need to solve it, you can have a joint understanding of the problem, and you can begin to develop a shared description of the decision and information use context to ensure that you understand the usability conditions. Some things that you can do are to engage in different exercises such as structured dialogues or mental modeling with stakeholders to get a good understanding of their context. And once you've identified the context and you have an understanding of the problem, you can move on to co-defining the project scope, what the priorities are for providing useful and usable information, and then develop concrete scientific research questions consistent with the decision information context, and then the problem definition. And you always want to make sure that you express these elements in a common language. Try not to use any disciplinary specific jargon when articulating these things. And then the last step is to adapt research methods and your approach to the specific problem and use context. And that simply looks like jointly developing a research plan after agreeing on and articulating the above in a common language. When it comes to the process itself, it's really important because people are coming from multiple perspectives to discuss any assumptions and make them explicit at the beginning. You also want to clearly articulate any concepts that are being brought to the project that are disciplinary specific. You want to bring up any assumptions that you might have about what you think is useful and usable for your stakeholder groups and discuss that to see whether or not you can validate those assumptions based on what the users and stakeholders actually want. And you should always be open to asking your stakeholders about whether your research is relevant and responsive to their needs continually throughout the process. You should also continually throughout the process revisit and revise your shared vision. You want to include in the design time for structured learning activities to ensure that you're actually co-creating. This can be shared learning when you're describing the use and or decision context, when you're determining the research approach, the form in which you'll present the data so that it's fit for the context, what type of qualitative translations you're going to provide, things like that. And you should always include users and stakeholders in your research decisions. And lastly, when it comes to the product, instead of providing more data or more accurate data, it's actually more important to provide data that is adequately contextualized and fits into the pre-existing structures of your stakeholder and user groups. You can also investigate suitable modes. You should investigate suitable modes for translation with your stakeholders. Some stakeholder groups might be best suited for using quantitative information given their decision context. Others might need figures or illustrations of changes or impacts, risk maps, things like that. Others might prefer something like a causal story in the form of a storyline about different possible futures that could result from different decisions that are open to them. And lastly, you should also always consider reaching out to someone who's an expert at knowledge integration or boundary spanner, who's somebody who actively bridges the gap between people that are producing knowledge and people that are using knowledge, because they can help with these activities and help you while you're still learning how to conduct actionable science and create actionable products. All right.
Great.
Okay, sorry, that was a lot. But
no, that was great, Monica. Thank you very much. And so we're actually kind of eating into our break. So if you have questions for Monica, please put them in the chat, and she'll have some time to respond to them over the break. And I just put one in there because I have a question for you. So we're going to take a break now. I did want to make sure people who may have joined late are aware that the 11 a.m. seminar has been canceled. And so we're actually going to shift our sort of informal lunch or informal gathering a little bit earlier. And you should have received an email from Elizabeth about that. But for now, we're going to take a break. So we'll take, let's see, how about a 10-minute break? And so we'll come back at 10:05 or 10:06, something like that, Mountain Time. And then we will have some discussion time. So yeah, and I don't know if anybody else wants to mention anything before we go on break. If not, I'll see everyone in about 10 minutes. Dave, were you planning to save the chat?
Yes.
Okay, that'd be great. There's lots of really interesting stuff there.
Yeah.
So I feel like,
Right. Well, the problem is that if we do go into breakouts, I think I can only save the chat for my breakout.
okay,
So, but I've at least saved the main chat now.
okay.
And then for the breakouts, it's easy to save the chat. So.
Okay, yeah, I see how to, yeah. I mean, hopefully, and I think it might be less of an issue with the breakouts, given that hopefully it's a small enough group, everybody's just talking and there's less of a use of the chat to communicate.
Sure, but yeah.
Yeah, no, but if there is stuff in the chat, it'd be nice to save it. So, yeah.
After this, for the informal lunch, tea, whatever it is, are we still going to the penthouse?
I was planning to go up there.
Okay.
So if anyone is at the Mesa Lab and would like to go sit in the same room at the penthouse, we should bring our laptops because we will just keep this Zoom call open and do it over Zoom. But yeah, but if anybody, I mean, at least then we're in the same room. I don't know. We've got to figure out a better way to do some sort of hybrid meetings, but yeah. Yeah, Monica, I agree with you about the funding mechanisms. I think that's one of the huge challenges here. And there's just doesn't seem like there's a lot of good avenues to give funds to do the prep work that's needed to do everything you were saying, developing research questions together, all those kinds of things that you need to do. And
yeah, and I mean, another thing that like I try to press upon Everett at least is that if you can't allocate like scientific based funding to these types of projects and things like that, then at least having a set of individuals that can serve as boundary spanners within your organization that can help to forge those connections and do kind of that preliminary work to set up and design projects is necessary because you can't just, I mean, like relying on NSF, right, to give you funding to do actionable or convergent work when so much of what they require in their proposals is like having thought out and done all of the preliminary stuff that you have to just do on your own in an unfunded manner. Like it doesn't really work because there's going to be other people competing for the funding that are at universities and can just get paid to do this type of stuff, do the preliminary work, and they'll have well thought out, really rigorous kind of proposals that you're competing with. And so it's really a crapshoot to be able, if you're like a project scientist, to be able to get funding to engage in this type of activity. And so since NCAR is placing so much emphasis on it, it's like, well, then you need to have structures in place to support the community of scientists that are seriously thinking about this, but that don't have resources allocated to them such that they can do the preliminary kind of setup and design that needs to be done to actually get started on the research process. So yeah, I don't know. I continue to try and poke them and tell them that they just need like a actionable convergent science center or something that consists of like maybe 3 or 4 people that are boundary spanners, have connections to these organizations and can like actually do the initial kind of integration that's needed so that these projects can actually be sustained and completed at an institution like NCAR. I mean, NOAA has stuff like that.
yeah.
So yeah, I don't know. We'll see. It always takes the institutional structures a while to catch up with science and how science is being done and the way that it's evolving, unfortunately.
Yeah.
Yeah, but I would look at organizations like GLISA, to be honest, right now. Because they already have relationships with stakeholder groups and they have an idea of what stakeholder groups want. And so communicating with them and allowing them to know what information you can provide, or what research activities you're engaging in, they can like start to make some of those connections for you. Yeah, so that's a pretty good resource. There aren't many boundary organizations though, unfortunately. And I think, if I'm not mistaken, GLISA is actually associated with NOAA. So you're using another institution's boundary organizations, which I don't know the
Monica,
politics about that.
could you say what GLISA is?
Oh, it's the Great Lakes Integrated Impact Assessment. I always get the acronym wrong. I'll put it in the chat. Great Lakes Integrated Science and Assessments. GLISA is actually University of Michigan. So it's within a university, but it's a boundary organization. So what it does is it works in the gap between decision makers, managers, and stuff in the Great Lakes region and climate scientists to try to forge connections and build relations between different scientific bodies and different policymakers or managers, so that the managers can get the information that they need to solve whatever problems they have related to climate in that Great Lakes region. And so they're essentially like the connectors or the integrators. And so those are boundary organizations. And those are, it is NOAA, never mind. It's just housed at University of Michigan. But there's like a Great Lakes initiative. There's a Midwest initiative. There is a Pacific Northwest one. And so there's a lot of these organizations, at least in the United States, that are like around a regional, and you can connect up with them. You have to do a little bit more work, I think, to find boundary organizations that are operating in international locations, but there are some. I know there's one for Pacific Islands. And WWA, which I think is water.
Western Water Assessment.
Yeah, Western Water. That's another great example. Yeah.
Thanks.
Thanks, Monica. I think we're mostly back, so we can move into our discussion and breakout section. The general theme for for this discussion is polar climate and land ice working group opportunities for CESM3. I'll give just a little background. CESM3 does not exist yet, but the plan, as I understand it, is to have a sort of preliminary working version of the model available in a little over a year from now, around summer 2023. And we know in broad outline what the components will be. Again, the workhorse version will probably be a roughly 1 degree model, but some of the components will be significantly different. In particular, the MOM6 model is the new ocean component. MOM6 will run on the standard configuration is a 2 to 2/3 degree grid, which is a bit finer than the POP model, which has been run at 1 degree. MOM6 has quite different, a different grid structure from POP, and is a bit more expensive to run per degree of freedom. So overall, the ocean component will be quite a bit more expensive than POP was. In the atmosphere, we'll have the next version of CAM. I think that'll be CAM 7. One of the major differences is that there will be a new dynamical core. I'm not sure the final decision has been made, but likely the spectral element dynamical core, which is used in VRCESM, which Tree spoke about. Also, there are vertical levels being added at the top of the model. So the next version of CAM will have better resolution in the upper atmosphere. The sea ice model will be size 6 point something, I think. Is that correct, Dave and Marika?
Yeah, maybe 7. I don't know.
We'll see. The land ice component will again be CESM, hopefully CESM 3.0 or 3 point something. And then we'll have the land model, which is now called CTSM. So again, those will have a sort of standard configuration of roughly 1 degree. which we'll likely use for CMIP 7 when that comes out. But there's also been a lot of interest in other configurations. For example, variable resolution configurations to focus on specific regions of interest, including potentially the Antarctic and the Arctic. A coarser resolution, which say 2 degrees, which we can run more efficiently for long time scales, especially for paleo simulations. So one of the things we'd like to talk about is, in addition to the standard configuration, what are the other configurations that we're most interested in, would be most useful for science? There's always interest in more configurations than we can support, at least at the beginning stages. So we want to prioritize what do we think are the most important things to focus on over the next year or two. And of course, there's always desires for more model development. And when the new model seems like it's still 2 or 3 years away, it seems like you can do just about anything. But as you get within the last year, you find that, okay, well, maybe we won't have time to do both of these things. So we need to prioritize there too. So as we go into breakouts, I think one of the working group co-chairs or liaisons will be, at least one will be in each breakout room. We'll go for breakout rooms that have about, I think, 5 or 6 or 7 people in them. And we'd like you to talk about what model developments you think are most important or most useful scientifically for CESM3, what model configurations you think should be supported, and finally, what are data sets that you'd be interested in using for assimilation, or data sets that should be generally made available to the community. Marika or others, is there anything you'd add to that?
No, I mean, that sounds good to me.
Okay, so so we'll have these last for about half an hour. So we'll come back at 45 minutes after the hour. We're not going to have official reporting sessions. The co-chairs and liaisons will take notes of their individual sessions, and we'll put our heads together later. But we will come back for a few minutes at the end. And if there's any points people would like to raise for the full group, you're definitely welcome to do so. And then we'll break again for a few minutes and come back at 11 for our Zoom coffee or tea. So with that, Elizabeth, would you like to go ahead and set up the breakouts? Okay, see you in half an hour.
So I'm glad, Ben, you were able to finish your sentence while we were kicked out.
Yeah, speaking really concisely, but yeah, that's the summary of how the interfaces work.
That's great.
I think everyone is back from the breakouts now.
I think we all got abruptly kicked out of our breakouts.
Yes, in mid-sentence, but that's okay. Were there any thoughts in the breakouts that people would like to share with the whole group?
I think one thing that came up right at the end of our breakout is that CESM has a huge number of simulations that a lot of people in the Polar Climate Working Group and Land Ice Working Group might not be aware of. So, predictability experiments, single forcing runs, the high resolution runs that were done under the IHESP project, all those kinds of things, and a better advertisement of all those runs might mean that there's some interesting polar science that gets done with them. So yeah, looks like Dave has something to say too.
Sure. I think, Tree was in the group, and so we talked a lot about the variable resolution development. And I think one of the things they brought up was the idea of having both Antarctica and Greenland at high resolution. And so I didn't know if that was sort of on the plate for CSM3 or not. And I think the thing is, when I think of that, I wonder, does that get so expensive where you're running both hemispheres with high resolution that you should just do the whole globe at high resolution? I mean, so where's the turning point there when you're talking about variable resolution? So,
And on a related issue there, Dave, is that assuming we go to the spectral element dicore, which has uniform grid spacing, if we have the same number of degrees of freedom globally, the tropics win and the poles lose, relatively speaking. And so one thing to decide is whether our workhorse grid should be finer than 1 degree in the Arctic and Antarctic. That wouldn't be technically high resolution, but it would at least be a break-even resolution compared to CSM2.
Well, but there's also a caveat there. I think the thing is, when we talk about variable resolution, there's a tendency to focus on the atmosphere here. and I mean, while getting increased atmospheric resolution is important, I think there's also the sea ice in the ocean and the land ice resolution as well. So, so I guess, do we do something where we have global high resolution atmosphere, but then regionally refine sea ice, ocean, and land ice? So.
Okay. Alice, you have your hand raised if you'd like to unmute.
Yeah. So several of the things we talked about were making it more usable, or the user friendliness of different configurations. So we talked some about nudging configurations, and we talked some about variable resolution as well, and like interest in coupling variable resolution. But then some of the same questions came up, like if you have a high resolution atmosphere but a low resolution ocean ice, is that valuable, or do you also need the high resolution ocean ice? So I don't necessarily think we have the solution for that, but we talked a lot too about having different structures that make it easier to use nudging, or easier to do like added heat experiments or something like that. And of course, I know anytime you want to make a model structure useful to use, that means like software engineering people time to make it usable. But I think that also dovetails with what Marika said about, I think it was Marika, someone said about, we have so many simulations, and I thought a lot about what Monica said too, is like, it's not necessarily that end users need the most improved physics, not that we shouldn't ever improve physics, but like we need to be thinking too about how we can use what we have and use that in a way that's useful for potentially stakeholders and stuff as well. whether that's advertising it or reframing it or figuring out like what's useful to them from that.
Gunter?
Yeah, I quickly want to, before I go into what we discussed in our breakout room, go back to what Dave said. Based on what Adam Harrington showed us about the new dicor resolution, it looked like the poles were losing pretty bad, and it's not about just increasing resolution on the ice sheets, but for the Arctic, we're thinking about using the variable resolution Arctic grid to like gain what we would lose with this spectral element dicor. And when it comes down to the CESM resolution, like CESM itself is not really impacted by the choice of the atmospheric grid because we use the same resolution. We use whatever resolution we want because we are, with a little black sheep here, like we don't follow, we don't need to follow what the atmosphere or the ocean tells us to do. So, and the idea of using a higher resolution or variable resolution on the poles is that the spectral element resolution would bring us back 5 years of all the effort we've gained so far. So I think there needs to be a push there. Now to shift what happened in our breakout room. So we were there with Kate, Jan, and Ben Johnson. And so we learned a lot about what CESL was doing with Drought for data assimilation. And while data assimilation might not be something we want to put into CSM3 for the ice sheet, we learned a lot about how it could happen, what we would need, and who would be the liaison from the CESL group to actually get this capability for CESM. So if there may be some interest like in the near future, maybe not right away, because we have already a lot on our plate, but I can see how this could be a topic of interest like in the next year or so.
I agree. I spoke to a potential postdoc recently about that. We'll see if something comes out of that project. I'll just add from our breakout, data assimilation came up, and one issue is that during the development process, often some model development is made and that breaks data assimilation, and then the data assimilation folks are left playing catch up, and the testing of data assimilation needs to be part of the ongoing model development testing. And another interesting point that came up is that because of CSM2's higher sensitivity, for some purposes, you're actually better off using CSM1 than CSM2. And so this is not CSM3 per se, but going forward, is there interest in having, well, something like what Zhangzhou has done for CSM2, where there's a paleo-calibrated version. Is that something we need to look at for future releases of CSM2, is having a model sensitivity which is, let's say, more consistent with paleo observations?
So I will add to that, the way I was understanding it in our breakout discussion was more like data assimilation for CESM as a standalone product, which
right.
Not necessarily like for a CSM3 coupled simulation, but one doesn't prevent the other. But since we have just so much data for ice sheets, there's just so far back we can go to do this.
Yeah, we can only assimilate for 2 or 3 years, right?
So doing data assimilation starting from pre-industrial, would be like, yeah, sure, but whatever you do is
but data assimilation going back to the 1990s, the satellite record would be great for land ice.
Right, but also used for spin-up purposes.
Yeah. Marika, you have your hand up.
Yeah, I just wanted to mention, we also in our breakout group discussed data assimilation, more focused on sea ice than land ice, but some of the things that came up were the value perhaps in assimilating freeboard and using things like ISAT2, which are measurements of freeboard, and also ice age, and using ice age products from like the National Snow and Ice Data Center, and assimilating those. So there was a couple people in the group that were data assimilation experts, and we thought it might be nice to have kind of more regular conversations between the people that are doing data assimilation with sea ice, the people that are developing the sea ice model, and trying to brainstorm about valuable products and valuable ways to assimilate data, et cetera. So, and that would go beyond the several people that were in the breakout group itself. But yeah, those were a couple of things that came up in data assimilation. I don't know if other people that were in my breakout group want to chime in on that topic, but. And we also, I'll just mention, we also mentioned or discussed a little bit about whether a variable resolution grid focused on both the Arctic and the Antarctic would be interesting. So, I don't know. We didn't come to a conclusion about how useful that would be. And I think it would probably depend on how expensive it is. So
how high is high for both poles?
We didn't discuss that either, but I mean, I guess, the kind of grids that True is showing for the Antarctic, and then the kind of grid that Adam has developed for the Arctic, and that you guys have been looking to look at Greenland ice sheet stuff. I can't remember what the resolutions of those are. And I don't know if anyone that was in the group
Quarter degree?
had an opinion on this, but yeah, Tree.
It's quarter degree for, I think it's quarter degree for Greenland as well. I think I remember that.
And then that's when these quarter degree global simulations came up that we do have available also under what was the IHASP project, where we had a quarter degree atmosphere coupled to a 10th degree ocean and sea ice, and that not many people are aware of those, or they haven't really been used very much for polar science kind of questions. So.
Partly because the sea ice looks crummy in those, but so the other interesting aspect of the resolution that I asked Tree in a question on as an aside is just how does the physics adapt when you go from coarse resolution to higher resolution parts of the domain, and it brings up tuning questions and and how do you tune a variable resolution version of a model? It could be very different from, say, a coarse resolution version and things like that. So it's a difficult problem to address. And I mean, it's not like the old days when we had the relative humidity thresholds for convection and things like that. But there are sort of other analogous physics knobs that change with resolution.
Kevin.
Yeah, related to that, in our group, we talked a bit about the vertical resolution as well as the horizontal, and how important that is for some processes. Sequan was interested in the higher resolution over Greenland and the boundary layer.
And I didn't say this earlier, but my understanding is that the version of CAM with more vertical layers will have more resolution near the boundary as well as up in the stratosphere.
That's my understanding as well, Bill.
Yeah, thanks. We've talked a lot about configurations, advertising, simulations available. Were there any new model developments that people are interested in? Things we should try to physically resolve that we don't now between now and CSM3? Or is it, I know for land ice, or at least I have a list of things, but what about for other components? Ed?
We didn't really have time to discuss this in the breakout room, but I did mention it yesterday. I think the wave sea ice interaction physics, if we can get that in CSM3, I think that'd be awesome.
I agree.
I think so. So we've just done some work, and there's a relationship, I think, for sea ice variability, especially maybe at high timescales, like kind of forecasting timescales, and even perhaps climate timescales. there's a paper that came out a few years ago that showed a relationship between the trends in wave height around Antarctica and Antarctic sea ice trends, and it was just a correlation, no causation type analysis, but and then at the high time scales, the kind of weather patterns that lead to fast sea ice loss also have bigger waves going into the sea ice, and we have no way now of simulating, okay, what is that added impact from the waves onto the ice pack? So I think it'd be really cool to be able to answer these questions.
Did you talk about what level development would be needed to do that?
So I know that because I'm in touch with Letty and Cici, I know that they have a ice ocean configuration that is including the wave watch coupling with the sea ice. But from what I understand, adding that to the fully coupled version has been a bigger challenge. And I don't know if Marika or Dave can. They probably know the details way better than I do. But I think being able to run like a fully coupled simulation, right, with the wave watch coupling and with the sea ice would be that'd be great.
Yeah, so wave watch is being coupled to CESM. I mean the later version and with the new caps. And Dave knows more about this. And I know Dave and Mariana Vertenstein, who's the head of our software engineering group, have been having conversations with Letty about getting her developments into the model. So I think there's a good likelihood that this stuff will get into CESM3. But I'll let Dave chime in because he's actually been more in the weeds with this than I have.
Yeah, well, I don't want to get down too much into the weeds, but I think it's a versioning issue. Most of the work that Letty has worked on is with size 5 and a slightly older version of WaveWatch, and so moving forward with these, it's bringing it to the forefront. It's also issues with WaveWatch and NOAA's plans for WaveWatch, and so there's a number of different technical issues there. However, they're not insurmountable. I think that we can still get through this and get it running in a coupled version very soon.
And my impression is that there's a very healthy collaboration with NOAA on this. So just, who are the ones who are the developers of WaveWatch. So that I think is promising.
I'll add here, Tree has a good comment in the chat that it's too reductive to say whatever resolution means the poles win. In some cases, changing the resolution means some regions of Antarctica could get better and others could get worse. And of course, it's not just resolution, it's also different kinds of physics, and it's complicated to get a good Antarctic simulation. Kevin?
Yeah, I'm wondering if people have opinions about how much work still needs to be done with clouds in the polar regions. Who wants to respond to that? Alice?
I don't have the answer, but this also came up. Ariel was in our group and we were talking about this. And one of the biggest questions we had is there's no one who really represents this here, but like what changes are going to be done in CAM or SEMA or whatever the thing is, and making sure that there's sufficient time to test that ahead of time. Because in addition to the Labrador Sea, the other issues that we came up with were like the aerosol interactions and how that impacted everything else. And so I don't know that I have the answer for you, Kevin, about your specific question, but that also was a concern in our group, is we don't really know what the CAM plans are, and to make sure we have time to test that, because that can really impact the sea ice and as well.
Actually, another thing I'd ask is how do we validate that for high elevation regions? Like, every single time I ask the question of like, okay, so what can I validate against? It's like, well, Calypso's got problems. Everything's got problems. So what counts as better than success? So maybe it's the same point I made earlier, but Yeah.
I'd say that, I mean, we use the cost simulator to enable comparisons with the satellite observations. And there like for CESM2, there's a couple papers, like Ellen McGilliton looked at clouds and their representation in the Arctic. I don't think she did anything on the Southern Ocean. So yeah, but I mean, I'm not an expert in this area. I'm sure there's more that can be done. I think it's great that people, like Jen Kay, Ariel have been looking a lot at the polar clouds. My impression is that they've improved, but they're still very challenging and they have a big impact on the surface radiation. So we care about it from the sea ice perspective, and I'm sure you care about it from the land ice perspective. So yeah.
Dave?
Yeah, and just to sort of changing topic, one of the other developments I'm interested in for CSM3 is the ice shelves. And I don't think we've talked about that at all this meeting, but I'm just sort of wondering what the latest plans are there, because one of the reasons to move to MOM and its new vertical coordinate is that we can then go under the ice shelves in the ocean model and so forth. So does anybody have updates or information on that? Or
I can try that. Well, first, and for those who aren't aware, MOM, because of its vertical coordinate, does allow the ocean to circulate under ice shelves, whereas POP circulation always ended with a vertical wall at the cabin front. So that's very exciting if you're interested in land ice, especially Antarctica. On the other hand, at 1 degree resolution, you typically only resolve the larger shelves well, like the Ross and the Filch-Nerani, and not the smaller shelves, which are also important. So I I think this is one reason among many that we'll want to have a high resolution Antarctic configuration, so that we can resolve some of the shelves of all sizes better. Then I guess one of the questions will be, where does the ice sheet model stop, or where does the ocean model stop and the ice sheet model start? It may be that at a given resolution, it may be that you do better by parameterizing subshelf melting, let's say within the ice sheet model and the ice sheet grid, given an ambient temperature salinity profile from the ocean at some distance away from the shelf. But the other option is to have the ocean model itself compute melt rates beneath an ice shelf, which is something that MOM6 can do. So I think we'll have to do a lot of testing to figure out whether the direct coupling or the more parameterized coupling between the ocean and the ice shelf works better. Keith?
Bill, I heard you refer to the high resolution Antarctic for doing these studies. And most of the pictures that I was seeing from the talks earlier had high resolution in the atmosphere. And Dave mentioned this as well about, well, what about high resolution in the ocean? And unless I'm mistaken, we don't actually have the ability to have regional refinement in MOM6, but it seems like people are talking about, well, we should use that.
Ah, right.
And I don't think we have that capability.
No. Sorry, we don't. Sorry?
We also don't have it in the SICE model. So just.
No, I guess I was thinking MOM6 has a 1/10 degree configuration, correct?
You can have a global high res,
a global,
or you can have a regional model.
Yes. So
MOM6 can be run regionally.
Yes,
but I don't know. I don't think we can do regional refinement.
That's correct. That's correct.
The only regional refinement is you could technically change the latitudinal spacing, which in the tripole grid gets weird at the top. But you could have enhanced latitudinal spacing around Antarctica.
I will mention that Gustavo
to some extent, yes.
I'll mention that Gustavo is working with a regional high resolution Antarctic configuration using MOM6. that's something we could try if we don't want to go to global, say 1/10 degree resolution. And for some purposes, even 1/10 degree resolution would not resolve eddy heat transfers onto the continental shelf of Antarctica as well as we would need to be realistic. So we would need some sort of parameterization at any feasible global resolution. Günther?
Yeah, I'm just wondering, like, how would this then work? Like, would we run one simulation, one CSM fully covered simulation with coarser resolution ocean to then use this as boundary condition for high resolution ocean Antarctica in Antarctica? I'm not clear about the possibilities, like, and how, like, what the workflow would be.
I think that's one possibility.
Is there another one that I'm not thinking about?
I've heard people say that MOM has the capability to nest within itself, but I'm not familiar with the details of that, how far that extends. I'm not sure we have. Does anyone here know about that?
I'm not aware of that.
So let's, I'll get together with Gustavo and try to find out more about that.
I do think, I mean, I'm not sure what the plans are with the high resolution configuration of the model, but, you know, because we often, when we run high resolution, we often are running older versions of the model. I think it, especially with moving to MOM, a global 10th degree ocean sea ice coupled to, you know, the equivalent of a 1/4 degree atmosphere, something like that, I think is a configuration that would be of interest. So,
but would likely be several times as expensive as
with BGC. Thanks.
Yeah, I think closer to 10 times as expensive is where you're headed on the 1/10 of a degree.
10 times as expensive as 1/10 degree pop.
Yep.
Yeah.
Yeah, I'm not saying that we would run this for, you know, a large ensemble, but we do run these kinds of configurations with CESM, previous CESM versions. I think having that capability with this new model, which has new capabilities with MOM, et cetera, et cetera. I mean, we might have to do fairly short simulations, but I think it would still be a good thing to have. And if we have biogeochemistry in it, then it's golden. So
or green.
You can, Keith, you can just keep your sign up the whole time.
It is worth noting, though, that the workhorse resolution of 2/3 of a degree in the ocean is definitely going to buy us some extra, you know, grid cells in the polar regions, you know, so it's, you know, so that's something at least. But I mean, I know in the Arctic it's a tripole configuration, so it's not that it's that much higher resolution, but even still 2/3 of a degree is better than 1 degree. So
we're coming up on a 1/4 past the hour. I don't want to cut off our time for casual conversation. Is there anything else before we break for tea? Okay, shall we take a few minutes break and then start gathering back in, let's say 20 past? Okay, so I'll just remind everybody, the land ice part of this meeting will be tomorrow between 8:30 and noon. So please come and join us for the last round of talks. Sorry, Ansi wasn't able to make it today, but hopefully she can do her seminar sometime in the near future. So we'll close the formal part of the meeting for today and then come back in 5 minutes or so for casual conversation and whatever you'd like to bring to eat or drink.